Here we go. We're starting chapter 10, section 3. We're going to talk all about alkanes. And alkanes have only carbons and hydrogens. They're like the simplest form of a hydrocarbon. And they're always going to follow this formula where however many carbons you have that same number times 2 plus 2 of hydrogens. So if you had 6 carbons, to determine the number of hydrogens, you would say 6 times 2, which is 12, plus 2, which would be 14. So that's always going to be true for all straight chain alkanes. And we'll talk about some things that are not straight chains that don't fit this rule. But if you're just talking about a plain old alkane, it will always fit that rule. And this tells us that alkanes are saturated hydrocarbons. They're nothing but carbons and hydrogens, and there are no carbon-carbon double bonds and no carbon-carbon triple bonds. So they're saturated with the maximum amount of hydrogens possible, which is why we call them saturated. So there are a lot of different ways that you can show formulas for organic compounds. There's actually 4 different ones that we're going to talk about. And so the most simple is just the molecular formula, just like we were talking about with our C6 example, right? So if I have C2H6, I know that's 2 carbons, and you can name it, and I'm going to teach you how to name it and all that kind of stuff. But let's say I go 2, 3, C4, and then I would say that would be H. 4 times 2 is 8, plus 2 gives me 10, so that would be H10. So you can pick any straight chain alkane, and if you know the number of carbons, you can know the molecular formula. Now, you could take that molecular formula into what's called a structural formula. This is what you learned as Lewis structure. It's the same thing. So you're just drawing out every single atom and every single bond. So just like what you've done in the past when you've drawn molecules, but we just call it a structural formula for alkanes. Then, because drawing a structural formula takes a lot of time, we really want some easier ways to do it. So here are 2 ways that we can do that. I don't know where that came from. That's weird. Okay, so a condensed formula shows us all the atoms in the molecule, and they're sequential. So if I look up here, if I could zoom out just a little bit, I have 2 carbons. The first carbon has 1, 2, 3 hydrogens. So that would be a CH3. And then the second carbon has 1, 2, 3 hydrogens. So that would be a CH3. So we're just writing them in sequential order. And we don't really put bonds. They're showing them here, but typically we don't. That way you can type them, right? You could write them without actually having to draw. So if you look here, this would be carbon. Look at our next example. We have, sorry, y'all. We have carbon 1. Carbon 1 has 1, 2, 3 hydrogens. So that's our CH3 here. Then carbon 2 has 1, 2 hydrogens. So that's a CH2. And then carbon 3 has 1, 2, 3 carbons. So that's a CH3. So you just put them in sequential order. Now, the line formula is really nice. And I don't know what that is. Let's see if I can get rid of that. There we go. Okay. The line formula is really nice because it's just less to draw. So basically what you do is you count the number of carbons you have in your chain. And each carbon in the structure, you just leave as basically the end of a line or an intersection of a line. So if you look at this very first example here, we only have 2 carbons, and I'm going to go ahead and put the dots in, and the dots correspond to the carbons. So if this is carbon 1 and that's carbon 2, this is carbon 1, this is carbon 2. And we assume that each of the carbons has the maximum number of hydrogens needed to complete its octet. So we can assume that carbon 1 has 3 hydrogens and assume that carbon 2 has 3 hydrogens. So you just don't draw them. All hydrogens are understood. So you don't draw hydrogens that are attached to carbons. Okay, so you just don't draw them. So look at your second example. This is carbon 1. Wow. This is carbon 1, 2, and 3. That's carbon 1, carbon 2, and carbon 3. So anything that's the end of a line or an intersection of two lines gives you a carbon. And that's all a line formula, or sometimes you call it a skeletal diagram. Skeletal diagram. It's the same thing. Okay, so now we're going to kind of talk about naming and properties and things like that. So some of y'all already know this. When you took my class, you should have learned this. When you're doing your alkanes, you have to be able to name them. So when you were naming covalent compounds and you gave those covalent compounds prefixes, these ones down here, well, it actually picks up with pentane here. Pent is going to mean 5, hex is 6, hept is 7, oct is 8, nonon 9, and decane is 10. So those are all the same as what you've learned in the past, but the top ones are different. So usually if you were naming ionic compounds, non-ionic, covalent compounds, you would say if there was only one, it would be mono. If there was 2, it would be di. But we don't do that for the first 4 carbons in alkanes. We call 1 meth, 2 eth, 3 prop, 4 bute. And so you have to learn those. And so the way that I learn the best is to use mnemonics. So I'm going to give you my mnemonic. And that is me eat peanut butter. And then I know that I'm going to pick up back in the old system. And I say me eat peanut butter in the pentagon. And so if you like close your eyes and see yourself eating your peanut butter sandwich in the pentagon, like it'll solidify for you. So you have to be able to go from molecular formula to here. This is the condensed formulas that we've been talking about so far. But you also have to understand that when we look at let's zoom in a little bit, a condensed formula where we have 2 things that repeat. What we can do is we can write that in a more condensed formula. I know, ridiculous, right? But you have a CH3 on the end, a CH3 on the end. So you have a CH3 on the end, a CH3 on the end, and then you have 2 CH2s. So we put a subscript 2 behind a CH2 in parentheses. So that's one of the cases where you'll use parentheses. There's another case to use parentheses, and I'll show you that later. But all you have to do is count how many CH2s you have, and that's your subscript outside of the parenthesis. And it just keeps repeating over and over and over again. Okay, so just realize that what those parentheses mean. Okay, so you have to be able to go from any one of these structures to any one of the other structures. So in this example, they're taking us from a line diagram or a line formula, and they want us to go to structural and condensed. And so what I like to do in order to get this right is I'm looking for the longest continuous chain of carbons, and that's my parent chain. So that's my longest continuous chain of carbons. And then I'm looking for things that kind of come off of it and just making sure that I don't lose them. So I count my carbons. I go 1, 2, 3, 4, 5. Okay, so I have 5 carbons in the main chain. So that's 1, 2, 3, 4, 5 carbons in the main chain. And then coming off of carbon number 2, I have 2 substituents. So there's 1 and there's 1. And then coming off of 4, I have a substituent, and that's where that carbon comes from. So count your carbons and keep track of your carbons. And then all you have to do is add the correct number of hydrogen atoms in order to complete their octet. So just remember that carbon needs 4 bonds. Okay. So if you look at, let's say, carbon number, hold on. Let's see, let me pick another color. If I look at carbon number 2 already has 1, 2, 3, 4 bonds. So if I come over and look at carbon number 2 over here, it doesn't need any hydrogens because it already has its complete octet. So just be careful about that and making sure that you give each carbon the correct number of hydrogens. All right. Then you also have to be able to draw the condensed formula. And it's kind of hard, I think, to go from this structure to the condensed. I think it's really kind of confusing. And I prefer to come back to this stick diagram. Okay, so I'm going to kind of erase a lot of stuff that I have written all over here. Okay, so the way that I do this is I just look at the stick and I say, okay, I have 5 carbons in a row, right? So 1, 2, 3, 4, 5. Now, look at carbon number 1. How many hydrogens does carbon number 1 need? Well, it's got 1 bond to a carbon, so it needs 3 hydrogens. So that would be a CH3. And I'm probably going to need a little more room. Okay, so I got a CH3. Then I go to carbon number 2. There's carbon number 2. It has 1, 2, 3, 4 bonds. So it doesn't need any hydrogens, but I do have to write my substituents. So coming off of carbon number 2, we're going to have to draw those 2, will include those 2 substituents. So the substituent is right here and right here. And so I'm going to write those, but I'm going to write those in parentheses. Ooh. Okay, so, and the nice thing that you can do is you can go 1, 2, 3, 4, 5, and you can just kind of keep track of your carbons this way. Okay, so let me put them in green because that's how I circled them up here. So I need to include these 2 substituents. What are those substituents? Well, each of these is a CH3. This is a CH3 because the end of a line is a carbon, and then the carbon has enough hydrogens to complete their octets. So I have, coming off of that second carbon, a CH3, but I've got 2 of them. So I'm just going to put it in parentheses and put a subscript 2 because I have 2 CH3s coming off of carbon number 2. Gosh, that sounds confusing. Okay, so then let's go on to carbon number 3. Carbon number 3 has 1, 2 bonds, so it needs 2 hydrogens. So I'm just going to write CH2. I get to carbon number 4. It has 1, 2, 3 bonds, so it needs 1 hydrogen. But I can't forget that I also have this substituent that's a CH3. So I'm going to have to squeeze that in there coming off of carbon 4. Ooh, I'm really running out of room. Okay, and I'm going to put a CH3, but I can't just leave it like that. It's a substituent, so I'm going to put it in parentheses. So these are the 2 reasons why you would use parentheses. Either you have a repeat in the main chain or you have a substituent. Either way, you use those parentheses. Okay, we got to pick up, not forget, carbon number 5. Carbon number 5 only has this 1 bond, so it is going to have 3 hydrogens attached to it. So, that's how I do it. I go straight from the stick diagram into the condensed formula. You're more than welcome to do it any way that works for you. Sometimes it's nice to draw it out and then to go to that condensed formula, but it's 6 to 1, half a dozen of another, however you want to do it. Okay. So remember how we said that carbon wants to make 4 bonds. That means that every single carbon that has 4 bonds, 4 single bonds, is going to be in the molecular shape of tetrahedral. So you've probably drawn Lewis dot structure before, that's A. If you looked at kind of like a surface diagram, that would be B. A lot of times we draw in 3 dimensions, but we have a 2-dimensional paper. So we say that these atoms are in the plane of the paper. And then this hydrogen is going behind. So this is behind. That's the dash. And then the wedge, this one right here, the wedge is going in front. So it's coming out towards you. So toward you. And it gives 3 dimensions to a 2-dimensional thing, right? The stick drawing is not the best, but it kind of sort of does the same thing. And then E is an actual ball and stick model, but it still looks 2-dimensional, but it's the same thing. All right. So let's kind of look at what happens when we start adding more carbons into a chain. And we start to see that if you're only given 2 carbons, right? So me eat, this is ethane. So that's 1, 2. So this is ethane. Oop. And then 1, 2, 3, 4. So that's me eat peanut butter. This is butane, right? And it's A and E. It always ends in A and E because I have only the A and E tells me I have all carbon-carbon single bonds. And then the S tells me I have 2 carbons. Okay, so each of the carbons that participates in these bonds, in these 4 single bonds, they all have tetrahedral shapes. And so if we start adding a bunch in line, like if we come down to butane down here, what we can see is this results in this kind of zigzaggy shape, which is why when we draw line diagrams, we draw this up, down, up, down, up, down, up, down. And then each of these places would be a carbon. So it doesn't matter how long your carbon chain gets, it's always going to have that characteristic up, down, up, down, up, down, up, down structure, which is why we draw line diagrams that way. Okay. And that really wasn't a molecule we were doing anything with, but I just wanted to show you that. All right. Now we have to kind of remember that carbon compounds can exist in a lot of different forms, right? The longer the carbon chain is, the more variations that chain can have. So let's give you an example. You could have C4H10 because 4 carbons, that's me eat peanut butter. So that's butane. So 1, 2, 3, 4. We could have this as a straight chain, and we would call this straight chain butane. But what if we took one of the carbons and moved it? Well, we would still have C4H10, but now carbon 4 would be attached to carbon 2. And so we would only have a 3-chain long. So me eat peanut, that's prop. And it's all carbon-carbon single bonds. And it's saying that there's a methyl group. So this is my methyl group. So methyl propane is an isomer of butane. It's the same molecular formula, but it's a different structure. So if you have this kind of an isomer, they're going to have different names. So this is called a structural. STRUCT, you are a structural isomer, right? You actually change the structure of the molecules, and therefore they'll have different names. So we really need to tie in the things that we were reminded of in kind of our review last time. So we know that isomers have the same molecular formula, but they have different names. But does that really affect their properties? So let's look at 3 different isomers of hexane. And so we're going to look at hexane, 2-methyl pentane, and 2,3-dimethyl butane. There's just so much going on in this figure. I just kind of want to narrow it down. So what I did is I just took these 3, and you can pause this video at any time. I took these 3 and I took the information from the table and I drew them. So the only thing you have to do is hexane is 1, 2, 3, 4, 5, 6, and it's all carbon-carbon single bonds. All right, so that's hexane. 2-methyl pentane. So I have 1, 2, 3, 4, 5 is pent. So pent means 5. A and E means all carbon-carbon single bonds. And then coming off of carbon number 2, you have a methyl group. And a methyl group is just a substituent with 1 carbon. So here's my methyl group. So what I see as I go from A to B is that instead of having something that's very spaghetti-like, I know I'm tying this into weird things. EHAGE, spaghetti. I think that's how to spell it. I don't know. I'm not a good speller. So spaghetti, if you think about a bowl of spaghetti, right? If you had a bowl of hexane, spaghetti is going to have lots and lots of contacts with the other strands of spaghetti. And so if you have something that is hexane, it's a hydrocarbon. The only intermolecular force that exists between molecules of hexane is London dispersion forces. So all hydrocarbons only have London dispersion forces. That's it. That's all they have. And remember, when we talked about London dispersion forces, we said they're really just rearrangements of the electron cloud, and that happens when the molecules bump into one another. So how often do strands of spaghetti in a bowl bump into one another? Gosh, a lot, right? So my hexane is going to have very, very, can I do this? High intermolecular forces, right? So we're going to have a relatively high boiling point. And that high boiling point relatively is 68.8 degrees Celsius. Go now to 2-methyl pentane. 2-methyl pentane isn't quite like a spaghetti strand, right? It's got a branch coming off of it. Instead of being one long chain, it's got a little branch coming off of it. And if I then go even and look at 2,3-dimethyl butane, but meaning 4, so that's 1, 2, 3, 4. It's all carbon-carbon single bonds, and then dimethyl. So 2,3-dimethyl. That's telling me that at carbon number 2 and carbon number 3, there's a methyl group. So I have a methyl group here and a methyl group here. So basically, hexane looks like spaghetti, and I'm going to say that 2,3-dimethyl butane looks like meatballs. So if you had a bowl of meatballs, how much contact do each of those meatballs have with one another? Not very much, right? They're not touching each other very much. So this has relatively low intermolecular forces. So it's going to have a low boiling point. And then 2-methyl pentane is somewhere in between, right? So as we go this way, we are decreasing our amount of intermolecular forces, and therefore we are decreasing our boiling point. And is that true? Well, I go from 68.8 to 60.9 to 51.1. So yes, that's true. So this is what you need to be able to do and analyze looking at a table like this. So it takes a little bit of practice, but you'll get it. Okay. So when we talk about hydrocarbons, all hydrocarbons, no matter what they are nonpolar. And remember, we said nonpolar molecules, they can only have London dispersion forces, right? So just kind of remember that's just London dispersion forces. All right, they're not water soluble. So that makes sense because water itself is polar. And so we know like dissolves like. So they'll only be soluble in non-polar organic solvents. So that works. They have low melting points and low boiling points compared to things like ionic compounds and things like that. So we'll see some examples of that in a little bit. Generally, they're less dense than water, so they'll float on water. But does this make sense? Sure. If you have, let's say, olive oil, and you're boiling a pot of spaghetti, who's ready for some spaghetti? Me. I could eat some spaghetti. Anyway, okay. So if I pour a little bit of olive oil in my pot of boiling water, right? What's going to happen? It's just going to float on the top. Even if I stir it a bunch, as soon as I stop stirring, it's all at the top and it all's kind of coming together. So it's lighter, it's less dense than water. As our length or molecular weight increases, our melting point and boiling points increase. And that's just thinking about the strands of spaghetti, right? So the longer the strand of spaghetti is, the more contact it's going to have with other long strands of spaghetti. So if you look up here, ooh, that was pretty far. Here, right? Here's our alkanes. And as we go down this way, right, we're increasing the number. We increase the number of carbons. So therefore, we increase the intermolecular forces present, and therefore we increase the boiling point. So it's those trends you should be able to recognize and account for. Okay. So now we're going to start talking about rules on naming. This is kind of a lot of detail, so just stick with it. So carbon atoms are classified according to the number of other carbon atoms that they're attached to. Because remember, carbons can be bonded to anything, right? In an alkane, they're only going to be bonded to either a carbon or a hydrogen. So if we look at the pink carbons in each of these examples, my pink carbon in this case, here's my pink carbon, is attached to only one other carbon. So we call it a primary carbon. Here, my pink carbon is attached to two other carbons, so it's a secondary carbon. Here, my pink carbon is attached to 2, 3 other carbons, so that would be a tertiary carbon. So it's just something to keep in mind, and this is going to be important in a little bit. So when we're naming compounds, remember how up here, where were we here? We were talking about this is methyl, right? But why are we using that YL? We're using that YL because we're saying that this is an alkyl group instead of a parent chain. So if I had a parent chain that's only one carbon, C1H4, right? Well, that's methane, CH4. I don't write the 1, you just write CH4. So that's methane. But if I have this carbon maybe attached to a long skeleton, right? Something else, this would be a methyl group. And so it's just telling you, is this the parent or is this the substituent? Substituent is anything coming off of the main chain. The parent is the main chain. And then substituent is something coming off of the main chain. Okay. So now if I had 2 carbons coming off of the main chain, and so instead of writing this whole big old thing, we just write R, and R means the rest of the molecule. Okay, so I'm just going to use the R from now on. I could have an ethyl group that, here's my parent chain. My R would be my, let's see if I can do this, my parent chain. And then my substituent would be all of this stuff. This is my substituent. This substituent is 2 carbons long, so this would be an ethyl group. And so your ethyl group, and these are all R's, right? Your ethyl group can be anywhere on the parent chain, and as long as it's 2 carbons coming off of the parent chain, then it's an ethyl group. The same thing is true no matter how many carbons long you get on those substituents. So if it's 1 carbon, it's a methyl group, 2 carbons ethyl, 3 propyl, 4 butyl, 5 pentyl. And it works with the same mnemonic, me eat peanut butter in the pentagon, right? It's the same thing. So when we're looking at these substituents, these alkyl groups, they're classified according to the number of carbons that are attached to the carbon atom that joins the alkyl group to the molecule. So what does that mean, right? The carbon atom that joins the alkyl group to a molecule, it's the one attached to the parent. So this is the carbon attached to the parent chain, right? And we said that parent chain, we're just doing as R. So here's the rest of the molecule. This is the parent. So my pink carbon right here, this is my carbon that's attached to the parent group. And if I look and I say, how many other carbons is this pink carbon attached to that's not in the parent? We're not counting the parent. There's only one. So this is a primary alkyl group. So then if I look at my next one, I still have my parent here. And then I'm going to look at my pink carbon. Here's my pink carbon right here. And I'm going to say it's attached to two other carbons within the substituent. So that's a secondary alkyl group. If I look here, here's my parent. And then I have my carbon that's attached to the parent. That's the pink one. And it is attached to 1, 2, 3 carbons within the substituent. So we call it a tertiary alkyl group. And I'm going to tell you why this is important. Your book's going to go over a bunch of slides that explains each one individually, but I think it's really confusing. So I'm going to teach it to you this way. This is the way I learned, and I really think it makes more sense. So when we talk about propyl and butyl groups, it starts to get a little bit confusing because propyl and butyl groups can have isomers. So if you're talking about just like a methyl group, like when we come up here and we were talking about a methyl group, there's only one way a methyl group can be, right? They're not bonded to any other carbons. So there's only one way it can be. The same thing is true about ethyl groups. It's always going to be 2 carbons in a row coming off of the parent chain, always. No other variation. But once you get to propyl and butyl groups, you can start having isomers. And so if you have, and remember, what does our R mean? Our R means the parent, right? That's what the R means. And so that means that this stuff is all the substituent, which is the alkyl group, KY alkyl group, right? Same thing. All right. So if there are 3 carbons in that substituent or in that alkyl group, we call that group a propyl group, which is cool. But now that we have 3 carbons in a row, we can actually have an isomer of the propyl group. And so a lot of times what you'll see is it's very commonly called isopropyl. And this is how it's like isopropyl alcohol, right? I know you've heard of that before. And so it's just talking about the substituent that's coming off. So we're saying that this is an isomer. Now, all that happened to make this isomer is the last carbon in the group came and bound to the first carbon in the group. If this one moved here, there's no difference. So that's not like a possibility. So it's only if the last carbon goes and bonds to the carbon that was bonded to the parent. So there's a common way to say that, which is isopropyl, and then there's a scientific way to say it. And so what we end up doing in the scientific way is that we call the substituent, we say, okay, within the substituent, there's like a parent chain within the substituent. So here's the parent chain in the substituent because it's the longest continuous chain. So there's 2 carbons in this longest continuous chain. So we call it ethyl, right? Because it's still a substituent. But then coming off of carbon number 1 is this methyl group. So we call it 1-methyl ethyl, and then we would name the parent, but we're not showing you what the parent is now. So that's just 2 different ways to do it, but they're both correct. One's common, one's, they call the standard way to name compounds the IUPAC way. Okay, when you get to butyl, there are a couple of different ways that butyl groups can be arranged. So we know in butyl, there's 4 carbons within the branch, me eat peanut butter. So if it's a straight chain, it's just a butyl group. And now you have to remember that I'm not showing you all of the hydrogens because it gets to be too confusing. So all we're doing is we're looking at carbons, but you do know that there are hydrogens that come off of each of these carbons. We just don't want to show them because it would just get so messy. Okay, so the first one is a regular old butyl group. If I took this last carbon and I plunked it down on that first carbon, I would call this, in the common terms, sec-butyl, because the carbon that's attached to the parent, that's the pink one, just like in the method that we did before. And we say that pink one, the one that's attached to the parent, is attached to two other carbons within the substituent parent. And so it's secondary, so we call it sec-butyl. So because the carbon, the pink carbon, right, is attached to two other carbons, so therefore it is secondary. The other way that you could do this is you could do this the IUPAC way, and you could say, okay, I have 1, 2, 3 carbons in the main parent chain, and coming off of carbon number 1 is a methyl group, so it's 1-methyl propyl. It's just, IUPAC or common. All right, now, the other way that I could do this is, instead of moving this last carbon, let's do it here, to carbon number 1, I could move it to carbon number 2. If I move that last carbon to carbon number 2, I'm going to get this structure down here. So this structure has that same, do you see this Y? It kind of looks like a Y. If I come up here, do you see how this kind of looks like a Y? So because this one is called isopropyl, this one is called isobutyl. So I just want you to kind of understand why the common one is isobutyl. They're all isomers, but they just call this one isobutyl because it looks like isopropyl. That's all it is. The IUPAC way is to go 1, 2, 3, and then have a methyl group coming off. And so that methyl group comes off of carbon number 2. So it's a methyl, and then there's 3 in the parent of the substituent. So that's propyl. Now, if we look at the last one, right, my pink carbon right here, this is the carbon that's attached to the parent chain, has, if we count them, 1, 2, 3, right, other carbons coming off of it. And so we call it tert, like for tertiary. So tertiary tert-butyl. Or you could name it the IUPAC way, and you could say in the parent there's 1, 2. So that would be ethyl. And then coming off of carbon 1 is a methyl, and then coming off of carbon 1 again is another methyl, and so we call it 1,1-dimethyl ethyl. You have to be familiar with the naming system for both. Okay, so I'm not going to go over their notes because you got it all on like one page. Okay, so that's all of their notes on that stuff. Okay, so now we can get into really naming. We know all the bits and pieces, right? So we're going to learn the IUPAC rules for naming. There's some common historical names that we kind of have to learn, but for the most part, we're going to stick to IUPAC. Okay, so we already know our prefixes, and we already know that anything with only carbons and hydrogens and no carbon-carbon double bonds or single bonds was going to end in A-N-E. So that's what we're going to stick with this time. So in order to do these, you have to know the rules. You have to write them in your own words, practice writing the rules so that when you get to problems, you know what to do. So the first step is to determine what's the parent. The parent is always going to be the longest continuous chain of atoms. It may bend, it may twist, it may start at the bottom, it may start from the right, it may start from the left, it may start from the top. It doesn't matter. But any carbon groups that are not part of this long chain are called substituents or branches. And they're also called alkyl groups. It's all the same thing. Okay, so let's look at an example. So what you want to do is you want to practice finding the longest continuous chain. So let's try a few things. A lot of people want to go, okay, from left to right, there we go. But that's only 1, 2, 3, 4, 5, 6 carbons long. What if, on the other hand, I started someplace else? Let me erase this. Woo, come on. There we go. What if I start from here? I'm not on highlight. Okay. That would be 3. Now, I'm not lifting my pen up. I'm just going to keep going. I come down and I have to decide, am I going to go in this direction or this direction? Well, whichever direction gives you the longer continuous chain, that's where you go. So I'm going to turn. I get to another fork in the road. Do I go up or do I go straight? You're always going to go towards the longer. So in this case, I'm going to go up. So this is how I find my longest continuous chain or my parent chain. Don't lift your pen up and try to find the longest route. Okay, let's do it again for the next one. Can I just go straight across? No, I can't do that. What if I start from the bottom and come up? I'm still on one chain. I'm still keep going. Okay, here's my first branch. Do I go up or do I continue to go straight? I'm going to continue to go straight. So this tells us we found our parent chain. Your next step is going to be to number the carbons in the parent chain. And so they have numbers, and I don't want you to see the numbers yet. So what I want to know is, do I start with number 1? Let me do this. Do I start with number 1 on this end, or do I start with number 1 on this end? Which one is it, the blue or the red? Well, let's do both and then decide. So we're going to number them 2, 3, 4, 5, 6, 7, 8. And that's in the starting from the left. If we start from the top, we're going to go 1, 2, 3, 4, 5, 6, 7, 8. So my question is, which one do I do? And the answer has to do with our substituents. So if I look at my substituents, I have 2 substituents. I have a methyl group and I have an ethyl group. So it doesn't matter which one's methyl, which one's ethyl. You want to give your substituents the lowest number possible. So if I start with my blue numbering system, my ethyl is going to be on carbon number 4, and my methyl is going to be on carbon number 6. So this is where my substituents are. They're on 4 and 6. If I do it in the red, my substituents are on 3 and 5. So I want to know which one is lower. That's the one I have to go with. So I have to go with the 3 and 5. So I'm going to stick with those red numbers, and I'm not going to use the blue ones. So you can go in and you can erase the blue numbers, right? And that's going to tell you the order that you should number your parent chain in. So I want you to pause the video and I want you to try it on this one. So go ahead and pause it and try it. So you should have tried it. And what you should have done is said, okay, I'm going to number from either side, right? And see what happens. So I'm going to go ahead and number 1, 2, 3, 4, 5, 6, 7 in red. And then I'm going to do blue and I'm going to go in the opposite direction. 1, 2, 3, 4, 5, 6, 7. So I only have one substituent on here, which makes it relatively easy, right? So in red, my substituent is at position 5. In blue, my substituent is at position number 3. So which one is smaller? That's going to be the blue. So I'm going to want to go with the blue numbering on this one. So I'm going to erase the red and I'm going to stick with the blue numbering. And that's exactly what they did here. They just have it already numbered for you, right? Okay. So now we're going to go on to the next step, right? We did number 2. We numbered them in the correct order, right? Okay. So now write each of the branches or the substituents in alphabetical order. So what do we mean by alphabetical order? Our substituents are like methyl, right? Ethyl, propyl, right? Those are examples. So what would come first alphabetically? The ethyl would come first, right? We want those to come first, except when we have halogens. So remember, that's our group 17, that's our chlorine and our fluorine and all of those elements, right? So you want to write the substituents in alphabetical order before the name. So I'm going to show you how to do this. And you have to tell where the substituents are using a number. And I'll show you this. And you separate numbers and letters with a hyphen and 2 or more numbers with with commas. So I'll show you some examples. So let's look here. So I want you to pause it. Well, first, let me tell you what to do. Find your longest continuous chain, number your longest continuous chain, and circle your substituents. Okay, pause it, go do that. All right, so you should have found your longest continuous chain. I'm going to start from here, and I'm going to get to here, and I'm going to go, oh, do I go up or do I keep going straight? And in this case, I keep going straight. I found another branch. Do I go up or do I go straight? It doesn't actually matter. I'm just going to go straight because it's easy. Okay, so I've done that, and I'm going to number my parent chain. There are 2 different ways that I could number it, right? I could number it 1, 2, 3, 4, 5, 6, or I could number it 1, 2, 3, 4, 5, 6. So I know I have 1, 2 substituents. So in the red, my substituents would be at 3 and 5. In blue, my substituents would be at 4 and 2. So 4 and 2 are smaller than 3 and 5. So I'm going to erase my red numbers. I'm going to get rid of that. Okay. So now that I have my parent chain, I've numbered my parent chain, I've identified where my substituents are, but what are my substituents? Well, a 2-carbon substituent, this would be an ethyl. And this ethyl is on carbon number, is coming off of the parent carbon at position number 4. So this would be 4-ethyl. I also have a methyl group because there's only 1 carbon there, and it's coming off of carbon number 2. So when I write this, I'm going to want to put them in alphabetical order. So I'm going to start, E comes before M. So I'm going to start, and I'm going to say 4, and I'm going to put a dash because there's always a dash between numbers and letters. So I'm going to say 4-ethyl, right? Then I'm going to have to put my other substituent. And so that's a letter and a number. So I need to do another dash. So 4-ethyl -2-methyl. And then I have to look at my parent and I go, okay, my parent is 6 carbons long. 6 is hex. So that's hex. And then A and E tells me I have all carbon-carbon double bond, carbon-carbon single bonds. So practice, 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 practice some more. So this one is a little bit trickier. Go ahead and pause it and try to name it on your own. All right, so I'm going to assume that you've tried to name it. So if I look at this, I'm going to look for my longest continuous chain. And to me, like, this is a long part. So that's a really good place to start. So if I go from here, the longest that I can get by continuing would be to go this way. So I would get 1, 2, 3 more carbons. Well, I know if I continue in the other direction, I can get more than 3 carbons. So I know I don't want to go up. I know I want to continue going this way. Okay, now I get a branch. Do I go to the CH or do I go down to the CH2? Well, the longest I could get would be 2 more. And I could get more if I go down, I could get 3 more. So there's my parent chain. Now I have to number it to give my substituents the lowest number possible. So I'm looking at this and I know, let's see, we'll do blue and red again. We'll go 1, 2, 3, 4. Let me do it on the bottom. 4, 5, 6, 7, 8, 9, or I could do 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. And then I have this is a substituent and this is a substituent. So if I do it in the red, my substituents are at 5 and 6. If I do it in blue, my substituents are at 4 and 5. So 4 and 5 are smaller than 5 and 6. So that's the one we're going to go with. So we are not going to go with the red. And I'm going to go ahead and erase the red numbers. So this is just our stepwise process. Okay, so now we have to name our substituents. So I have 3 carbons. I'm looking at this one right here. I see I have 3 carbons. 3 carbons is a propyl group. But do you see this like Y shape, right? It's not a normal propyl group. A normal propyl group would be like if I didn't have this CH3 here and I had another CH3, right? That would be a regular old propyl group. But this is an isomer, so this is isopropyl. And that is coming off of carbon number 4. So this would be 4 isopropyl. Then I have another group. There's 4 carbons in the group. 4 carbons would be butyl, butyl. And if I look at this carbon here, this is the carbon that's bound to the parent. And I say it's bound to 1, 2 other carbons, right? That would be the sec butyl because it's a secondary. So I'm using the common. You could go back and do the IUPAC if you wanted. But now we have to look at our prefixes to know who comes first and who comes second. So I'm looking at the P and I'm looking at the B. So B is going to come first. P is going to come second. We don't look at those iso and sec. We don't count those. We're looking at the P and the B. So we're going to say it's, oh, and I didn't write that. Haha. My sec butyl is coming off of carbon number 5. So I would call that 5 sec butyl, 4 isopropyl. And then my parent is 9, which is non. And then it ends in ANE because it's all carbon-carbon single bonds. So you just got to practice. You got to practice. So when you have a substituent where you have more than one of the same substituent, you're going to use a prefix like di, tri, tetra, and then you list the number of the carbon where those substituents are. And so 3,4-dimethyl tells me that on carbon number 3 and on carbon number 4, they each have a methyl group. Whereas here on carbon number 4, and carbon number 6, each one of those is an ethyl group. So there are 3 ethyl groups. So pause it and try to name this one. So what you should have come up with is, here is our parent chain right here. And then you should have come up with numbering it in this direction, 1, 2, 3, 4, 5, 6, 7. And then you have a methyl, and an ethyl. So this is a methyl, At 2, this is a methyl. At 3, this is an ethyl. At 5. So then we're going to look at our first letters in order to determine alphabetically which way we're going to do that. E comes before M, so that's E and M, right? So we're going to say it's 5-ethyl. So 5 dash, make sure you put those dashes in there. 5-ethyl, 2 dash, then methyl. We have 2 methyl groups. So we're going to say on carbon number 2 and carbon number 3, there are methyl groups. And so that's why we have to put that dye in. And then it's heptane for 7, right? So just remember you're alphabetizing based on the name of the methyl group, not how many there are. So go ahead, try again, try another one. This is all about practice. Practice, practice, practice. Okay, pause it and try. Okay, so here you should have found your parent, and yeah, looks like that. Okay, so now I'm going to number it to give my substituents the lowest number possible. 3, 4, 5, 6, 7, 8, 9, 10. All right, and then I've got a methyl group. At 3, I've got here, this is an isobutyl. Butyl, and that's coming off of carbon number 6. And then also coming off of carbon number 6, I have an ethyl group. So then when I'm trying to alphabetize, I want to be looking at my M, my E, and my B. So what comes first? They didn't do it right. Oh my God, they didn't do it right. It should be 6-isobutyl, then dash 6-ethyl, then dash 3,3-dimethyldecaine. I mean, I wouldn't mark it wrong either way, but you're really comparing the butyl, the ethyl, and the and the methyl. But I mean, either way is okay for the isobutyl. I would accept it either way because isobutyl is not actually butane, right? Me eat peanut butter, but it's fine. Either way I'll take. So either or, I'll take it either way. But technically the bottom one's better. Anyway. Then also you have to be able to go in the opposite direction. You have to be given a name and be able to go to the structure. So when you're looking at a name, you know that this is a substituent. So coming off of carbon number 1, you have a bromo. What is bromo? It's just bromine. Anytime you have a halogen, that's how they do it. They say bromo, iodo, chloro, all of that. Then coming off of carbon 4, we have a methyl group. So carbon number 4 is a methyl. And then hexane, hex is going to tell me that I have 6 carbons in the parent. And then A and E tells me all carbon-carbon single bonds. And I'm telling you, it really helps to write all this stuff down. And then when you draw it, you can come back and go, okay, I'm just checking things off. So here they drew the 6 carbon parent. Then they added a bromine, and I would say you really need to number your carbons. 4, 5, 6. When you're drawing this on paper, you need to number your carbons. It's just, you're just going to be so much more successful. 3, 4, 5, 6. So now I can see coming off of carbon number 1, I need a bromo group. There's carbon number 1's bromo group. Then coming off of carbon number 4, I have my methyl group. And then all you have to do is add hydrogens to complete everybody's octet. And then you can draw your condensed formula, you can draw your skeletal formula, whatever's being asked of you. Okay, and the last thing we're going to talk about are structural isomers. So remember how structural isomers are different in how they're connected. So they're going to have different names, and therefore they're going to have different properties. But this is really easy. This is the spaghetti. which has lots of contacts. So it's going to have high intermolecular forces, which means it's going to have a relatively high boiling point, relatively high melting point. So if I look over here, this is more the meatballs. And meatballs has less intermolecular forces, lower intermolecular forces, therefore a lower boiling point. It's more negative, and a lower melting point. It's again more negative. So that makes sense. All right, that is the end of section 3.